Okay, so tangent as a limit of secants. Now, this is the introduction to basically how we're going to differentiate most of the graphs, if not all of the graphs, that we are going to be looking at. Now, there's going to be hints and tricks and tips later on in the topic on how to do it much quicker, but this is sort of like the how to do it, okay? So what we're going to do is we've got this graph of, it's approximately y is equal to x squared. So what we're going to do is we're going to let, okay, p of x and f of x, okay, so this is going to be our defining point, and what we're going to do is we're going to let q, so another point, and it's going to be any other point on the curve to the left or right of p, okay, so, you know, let's say p is here, then q can be up here, or q can be down here. Doesn't really matter where q is, but let's, you know, for the sakes of this, let's put it somewhere where it's going to make it nicer. Actually, you know what I'll do? I'll put P down here, and I'll put Q up here. So we typically like Q on the right of P. Now this works either way though, but Q is easier. It's easier to work with Q when it's on the right. Now, what we're going to do is, it's going to be on the left, right, and it's going to have X coordinate, X plus H, okay? So, you know, if P is here at X, okay, let's pretend that's not at the 1, let's pretend, let's say P is here, okay? Then it's at x, so some value of x, okay, then q is going to be h further than x, okay, so we're going to say, well, this value here is x plus h, okay, so the distance from here to here is some value, okay, we don't know what exactly that value is, but let's just call it h value. And then with that being said, you know, so if this is our function value at x, so the value of the function at x, then the y coordinate will be, you know, f of x plus h, because we're going to be essentially putting that into our function to get, well, how high up is this function, okay? So if it's h more along, then the function value is h more greater. Okay, so what we're going to do, okay, is then say, okay, so I'm going to define those 2 points. Okay, then the gradient of the secant, so if I was to draw a secant between these 2 points, okay, so remember it's a line that goes through the two, and I'm going to try my best to draw this one as to the best as I can. So let's go like that. And I'm going to cheat. So you can kind of see that this one's going to go through like that. Okay, and I'm just going to zoom in heaps. So as you can see, you know, it's really hard to do this with here, but we've got like a difference between the two, okay? So it's not exactly, you know, on the line, like there's this bit of a gap between the two, but it's the point that's going to make the secant, okay? Now, what we're going to do is we are going to take the gradient of this secant, okay? So the gradient of this secant is just the rise over the run. So it's going to be this vertical, didn't like that. Okay, it's going to be this vertical rise between P and Q, and this vertical run between P and Q, okay? Now, we know that the gradient of the secant, okay? And it's going to be the rise over the run, okay, the rise over the run. And this rise over run is, well, our rise is just the difference between f of x plus h and f of x, okay? So from q, if q is f of x plus h and f is f of x, okay, it's just the difference between those two. And my run, well, it's just the difference between x plus h and x. So that one's just h. So my rise over run, my gradient, is equal to f of x plus h minus f of x over h, okay? And so the idea is that to find, so this is not the tangent, mind you, this is a secant, okay? It's the gradient between those 2 points. But to find a derivative, we need the gradient of a tangent. So, well, let's just say we slowly start moving this Q closer and closer and closer to the point of P. Okay, so if we start moving this one closer and closer and closer, or we start to approach a difference, so this H value here, so this one starts getting closer and closer and closer to the X. So as the H starts approaching 0, so the difference between the X and the X plus H gets closer and closer to 0. So what we do is, as H approaches 0, the point Q moves along, and it goes closer and closer, and as close as we want it to P, and the gradient of the secant PQ becomes as close as we like to the gradient of the tangent at P. Now, it's not exactly the tangent, but it's so bloody close to the tangent that we may as well use it. So hence the gradient, of tangent, the gradient of tangent at P is equal to the limit as H approaches 0. So this is our limit notation, and this is why limits, and it was very important to learn about limits. So as we get closer and closer, so as that Q gets closer and closer and closer, as that H gap gets smaller and smaller and smaller, okay, f of x plus h minus f of x over h. So the gradient at the tangent at P is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so that's how we're going to find the derivative. Okay, so continuing on, okay, the derivative as a limit. So for each value of x, okay, the derivative is defined as this. Okay, so we can define the derivative. So define the derivative as f dash of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So whatever your function is, you can use basically what is a formula to work out what the derivative is going to be. Okay. Now the above limit formula to find the derivative, this is called first principles of differentiation. Now, whenever you're asked to use first principles to differentiate something, you have to use this formula. That's what we're asking you to do. Later on, you're going to learn tricks that's going to make this much quicker to actually find a derivative. But whenever you have to use first principles, you must use this, otherwise you will get 0 marks. So with that being said, let's jump into our first example. So example 1, for f of x is equal to 3x squared, use first principles differentiation to show that f dash of 5 is equal to 30. So to do so, we're going to use that formula that we used before. So I'm going to write that formula again. So we need to add that limit bit. So it's the limit as h approaches 0 of f of x, so this is f dash of x is equal to, of f of x plus h minus f of x over h. So what we're going to do is we're going to substitute the value of 5 into this. So we're going to do f dash of 5, okay? So that's going to be equal to, now we don't have to write the limit for this bit, but we need to just put in the rest. So f of x plus h, so that's going to be f of 5 plus h, okay, minus f of 5 over h, okay? So just replacing the x's with the 5's. Now, so our equation, or our function, is 3x squared. So this is the function that we're using, okay? So we're going to replace the x in this function with 5 plus h. So to do so, we're going to go 3 lots of 5 plus h all squared minus 3 lots of 5 squared over h, okay? Now we're going to expand this one out. So 3 lots of 5 plus h all squared, well, that's 25 plus 10h plus h squared, okay, minus 3 lots of 25 all over h. And I'm going to do that all over h, okay? Now, expanding this out even further, we get 75 plus 30h plus 3h squared minus 75 over h. Okay, cancelling out, we've got this 75 and this minus 75 here. Okay, so continuing on, we get 30h plus 3h squared divided by h. We've got a common factor of h, so it's h30 plus 3h all over h. Okay, the h is going to cancel out now. I'm not going to do all this working out for the next lot of ones either, by the way. And we get 30 plus 3h. Now remember, back up here we said we've got a limit when h approaches 0. Now we could put in a really tiny number and get a answer that's going to be very close to what the actual derivative is. But as h approaches 0, what happens to this thing here? Well, 30 doesn't get touched, but as h approaches 0, well, let's try it. 3 times h. So 3 times, let's start with 3 times, well, if h was 1, okay, it would be 3, so it'd be 30 plus 3. But if h was 0.5, then it's 3 on 2 or 1.5, okay, so it'd be 30.15. 0.25, which is a quarter, so 3 quarters, 0.1, which is 3/10, 0.01, okay, which is 3/100. Like, you see what the picture is. Like, what happens when I'm getting really close is I'm getting a number that's very close to 0. So it's almost negligible, okay? So with that, as h approaches 0, this thing, we can pretty much say it's going to disappear, okay? And that's going to leave us with this 30. So our derivative of 5 is 30, okay? So it's kind of a lot of working out, and it's going to take a bit to get used to, but we're basically just using our understanding of functions into a formula to get the derivative back out using that formula. Now, for part B, we're going to use some we're going to do pretty much the exact same thing, okay? Except what we're going to use is we're going to do it for just f dash of x. So I'm going to use first principles to do this one. So it's f of x plus h minus f of x over h. And our function is equal to 3x squared. Okay, so wherever I see an x, I'm going to... So for the first bit, whenever I see an x in my original function, I'm going to replace it with x plus h. So we're going to get 3 lots of x plus h squared minus 3x squared over h, okay? So that's just replacing x plus h into here, into the x's in here, and replacing the x's into there, which doesn't actually change anything. But that's what we're doing, okay? So expanding this one out, we're going to get 3 lots of x squared plus 2xh plus h squared minus 3x squared over h, okay? So expanding that out, we get 3x squared plus 6xh plus h squared minus 3x squared all over h. Okay, doing some clever little cancelling. We've got a positive and a negative 3x squared, so they're going to cancel out. We're left with 6h plus h squared over h, okay? The h's are going to cancel out there, and we've got 6x plus h. Now, as h approaches 0, okay, the h on this one is going to be pretty much negligible, okay, and so that's going to leave us with the derivative of the function is equal to 6x. Okay, so the derivative of this function, 3x squared, is equal to 6x. Now, part 2 of this part B, so I better put the part 1 up here. So part 2 says substitute x is equal to 5 to confirm that f dash of x is equal to 30. So sub x equals 5 into f dash of x, and we get 6 lots of 5, which is equal to 30, which is the same as above. Therefore, f dash of x equals 6x is the derivative. And this is more like the generalized derivative. The derivative of f of x is equal to 3x squared. Now, if I asked you to put another point in, so let's say instead of subbing x is equal to 5, we did x is equal to 10, which would give us 60. So that's the rate at which the graph is increasing at that point. We could substitute that in and we could get 60 back out, but you could then do it the long way by putting 60 into here as well, doing all of the algebra, and you'd get 60 down the bottom. Okay, so with that being said, that's going to be the end of the first video, the derivative as a limit. And we have one more video to do, which is finding points on a curve with a given gradient.